In the UK, for the year April 2021 to March 2022, the Office of Road and Rail official statistics show a total of 14 mainline, potentially high-risk train accidents. Out of these 14, 5 are listed as derailment under type. This is 35%. PHRTA is defined as accidents that have the greatest risk of resulting in physical injury. The other type of incidents that fall under the PHRTA bracket are train collisions with other trains, trains colliding with cars at level crossings, or buffer stop strikes. This statistic shows that derailments are still a major risk, especially when you consider that a number of the other categories have external factors, such as cars on public roads, as a major input. Although the data is not broken down to include the causes of the derailment, it is an accepted fact that switches are a high risk and the leading cause of derailments, particularly at switch entry and through the planed or machined length. This is due to a number of factors, such as the function of switches requires them to move, introducing variations in a number of areas that are not experienced in plain line. This can include the setup of the POE and the fact that the switchblade has a degree of freedom in its movement. The varying nature of both the profile of the switchblade and the geometry of the turnout lead to varying wheel-rail interfaces and forces in a short area. Switchblades are a lot more likely to be damaged, given that they are thin in profile towards the toes. Switchblades and the stock rails can experience different rates of wear depending on the usage patterns. Switchblades, particularly on tight radius turnouts, are subjected to large forces as they turn the train. Most derailments of switches that aren't caused by operator error have the condition or profile of the rail as a factor. From the Network Rail Standard, the inspection and repair to control the risk of derailment at switches, also known as 053 after its document number, there are 2 main types of derailment mechanisms within S&C. First, the flange climb derailment, where the wheel climbs up the gauge side of the switch rail. Second, the frontal derailment, where the wheel climbs up the front of the switch toe and onto the top of the switch. These mechanisms are typically caused by the interaction of the wheel with a switch rail that is worn or damaged and often not lubricated. Let's take a look at these in turn. So firstly, the flange climb derailment. This type of derailment is when, under the right conditions, a wheel climbs up the face of the rail. To understand how this can happen, we need to look into the forces acting on the wheel. The 2 main forces on the wheel are the vertical force acting down from the mass or weight of the train, and the lateral force resulting from the train moving around the curve of the switch. The vertical forces, known as Q, are keeping the train wheel tread sitting on the rail. This force is in contrast to the lateral force that is pushing the wheel sideways and over the rail. There are 2 other factors to throw into the mix here. First is the wheel-rail contact angle, and secondly, the friction between the wheel and the rail. The contact angle is important because it's key in the direction of the resultant or overall force from the Q and Y forces. The friction element is also important because a high level of friction allows the wheel to gain purchase or traction on the switch rail face, making it easier to travel in an upwards direction. So how are all of these elements pulled together and the overall risk quantified? The answer is Nadal's formula. This formula is a ratio between the Y and Q forces, and can also define a limit to this ratio, which, if exceeded, increases the risk of a flange climb derailment. Let's have a quick look at how this critical or maximum safety ratio is calculated. Our list of variables is shown on the right-hand side, and are all the forces and factors we've already discussed. Let's put these on the diagram to show where they all are. Here we're solving for Q crit, which is our critical load. You can see that trigonometry is required due to the angles involved. This overall ratio of Y over Q crit gives us what is known as Nadal's limit. I do not intend to go further into the maths on this, but we will look at what this equation tells us about how the changes in the different factors affect the risk of derailment. Let's look at the ways the derailment risk can be reduced. Firstly, to increase the contact angle between the wheel and the rail, or making the switch closer to vertical. This makes it harder for the wheel to climb the rail without slipping back down. The risk of the wheel climbing can be further reduced by reducing the amount of friction between the wheel and the rail. This is done by ensuring the switch rail surface is adequately lubricated. These 2 things form a foundational part of inspection and maintenance regimes of switches, which we will look into further later in this video. But what about the forces? How does a change in Q and Y affect the derailment risk? The ratio between Y and Q is increased if the vertical load Q is reduced, or the lateral load Y is increased. The most common way this can occur is a track fault, such as a twist, either close to or within the switches. These geometry faults change, for a short distance or period of time, the forces. Twists and voiding especially lead to a load and unload cycle of the wheel, which reduces the vertical force temporarily. The sharper the turnout radius, the higher the lateral forces, for two reasons. First, the angular velocity of the train increases, wanting to push it outwards. Secondly, what is known as the angle of attack of the wheel sets increases. In straight track, the flanges of the wheel run parallel to the running face of the rail. When on a curve or within a switch, the wheels run at an angle to the rail. The outer wheel is then angled into the rail, attacking it and trying to climb it. As the radius tightens or becomes smaller, this angle increases further. This is why shorter switches are at more of a risk of derailment. So let's move on to the second derailment mechanism. This is the frontal derailment. A frontal derailment occurs when the train is making a facing move. This is when the train is travelling into the toes of the switches. The 053 standard identifies 5 hazards that can provide the means for a frontal derailment to occur. It also gives telltales to an inspector of what they might see and associated with these hazards. The hazards can each, or in combination, lead to a ramp being created at the toe, allowing the wheel to travel up and over the stock rail. It could derail fully, or fall into the gap between the switch and the stock rail, splitting the points. Damage to a switchblade along a length and to a certain depth can also allow a wheel to effectively pass through the switchblade, again splitting the points. Let's go through these hazards. Each hazard has an overall condition followed by the key telltales. Hazards 1, 2, 3 and 5 all relate to the wheel position on the rail and the interaction that can lead to derailment. You'll also see through this that sidewear is a particular issue. First up, hazard number 1 is a side-worn stock rail with a little used switch. The telltale signs for this are: the top of the switch rail projects above the sidewear scar on the stock rail, the switch tip has been struck by wheels, the switch rail top deformed by wheel contact to match the shape of the stock. Hazard number 2. Hazard number 2 is the stock rail and switch rail are both side-worn. Telltale signs of this are: train wheels have formed a ramp on the switch rail, and markings where a wheel has climbed the switch rail and then slipped back down. Hazard 3 is a stock rail headwear associated with a less head-worn switch rail. The telltale signs on this are again a switch toe that's been struck by the wheels, or signs of flange climb within 40 mm of the toe. Hazard number 4 is switch rail damage, and this comes in a number of ways, forms, and has different telltales. Lipping is present along the gauge face of the stock rail and or along the rear of the switch rail. Lipping might also be present on the gauge face of the switch rail. There could also be evidence of horizontal longitudinal cracking under the lip of the switch rail, visible horizontal longitudinal cracking near the top of the rear face of the switch rail, small pieces of metal starting to break off of the switch rail, several pieces of broken out switch rail, or a seating gap under the switch rail associated with lipping components. Further damage can be caused by not treating the lipping, especially on the stock rail, as it will get dragged and pulled off by a passing train wheel. Hazard 5 is a switch rail with sharp facets on the running edge radius. So the telltales of this are any profile forming a noticeable pronounced edge or facet on the switch rail running edge radius. You may see dust or shavings of steel in the proximity of the switch, or bright marks indicating wheel contacts with a sharp radius. So how are all of these hazards and the 2 derailment mechanisms controlled to stop trains derailing? This is through an effective inspection regime. Switches need to be inspected to monitor the key factors we've seen in this video. The inspections will, through the use of gauges to mimic the train wheel, determine the contact angle. This has to be 60 degrees or greater. You'll also look for any of the telltale signs of the 5 derailment hazards that we've been through. This is through visual means as well as the use of other gauges. You'll have noticed that sidewear was mentioned a lot as part of the 5 hazards. Therefore, the level of sidewear on both the switch and the stock is monitored. Lastly, switches should be lubricated at regular intervals to help keep the QY ratio below the limit. The frequency of these inspections can vary based on the switch's characteristics and defect history. Switches with tight radii, such as short or similar flexure switches, as we discussed earlier, are more at risk, so therefore need more regular inspection. The ways switches are used, such as ones that are predominantly used in a single direction, can also be a higher risk. Reviews of records and defect trends can identify specific switches that are more susceptible to defects, so require closer monitoring. These hazards can also be removed in three main ways: grinding of the switch to correct its profile and the contact angle and remove lipping, weld repair to the switch to increase its height or remove any damage, and ultimately replacing the half set of switches. So now you know the two main ways a train can derail over switches, the reasons why, and the hazards to look out for if you ever find yourself looking at a set of switches. If you have any questions, do drop them in the comments below and I'll try my best to answer. Please take a second to hit that subscribe button to keep up to date with all of my videos as they are released. Please also drop us a like if you found this video useful. Thank you for watching.